Hello everyone, and welcome to the last day of this FDP. Uh, it uh, has been my honor to come in here and discuss the ideas around quantum computing. And we will be specifically today we will be specifically seeing the current trends, the challenges and the limitations that are there with quantum computing, and what exactly is uh, going around in different say circuits of uh, with respect to the software and the hardware phase. So let me just share my screen first. I hope my screen is visible. Ma'am, can you confirm, please?
Yes, sir, it is visible.
Okay. Thank you, ma'am. Now, uh, this is where everything from the week comes together. Till this point, we have built the concepts on day one itself, where we discussed about the ideas of some basic fundamentals, like what is a qubit, how it is different from a bit, that is a classical bit, what exactly is superposition, the starting point, you can say the starting idea, very fundamental idea, how the bits that we have, the classical bits, they go into when we apply a Hadamard gate, how they go into superposition. That is until unless we measure them. So the idea of superposition and the idea of measurement, very important, profound idea. And this measurement is one of the ideas in quantum computing that is non-reversible, that we can't reverse it. Then we had seen another concept, that is interference, and the idea of entanglement. And around this ideas, we focused on some basic mathematical understanding of how a qubit actually behaves, what is the idea of amplitude, what is phase, and the two different types of phase, global and relative phase. We uh, discussed briefly in the idea of these concepts. This was discussed on day one. Then on day two, we tried to build some circuits, and the circuits were powered by the idea of how quantum states and quantum gates were applied. So the idea of single qubit gates and multiple qubit gates we discussed by and large in the whole session. The how single qubit gates like poly XYZ gates and Hadamard gate, S and T phase gates, how they actually behave, and the idea of multi-qubit gates, how it gives rise to the understanding of the mathematical foundation behind tensor product. And tensor product is the basic idea around multiple qubit gates, and what exactly we mean by the product states and the entangled states uh, pertaining to the idea of entanglement. So This is what we discussed around the idea of the circuits. Then on third day, uh, we focused on the algorithms, the basic quantum algorithms, where we discussed the proof of concept algorithms, namely the Deuce algorithm, Deuce-Stosa algorithm, Bernstein-Vazirani, and a little bit idea about Simon's algorithm also. Besides these algorithms, we also focused on two more algorithms that have a good amount of application in various areas, uh, namely the first algorithm, the Grover's algorithm, where it is used for unstructured search, and the Shor's algorithm, it is used for uh, the cryptographic ideas. And then the fourth day, that is yesterday, we discussed about the variational method, at how variational quantum computing uh, is revolutionizing the two eras that we discussed, two different eras. So, era one was pertaining to the long-term uh, coherence, that how the algorithms like Grover's algorithm and Shor's algorithm will uh, set a defining moment when we have good fault tolerant computers. Although this Grover and Shor, the algorithms like Grover and Shor are exact, they are provable, but uh, we need some fault tolerant quantum computing to handle them. Although right now we are living in the NISQ era, as we discussed, and today we will have a good discussion around what exactly is happening in NISQ and all. So the noisy era. So how we can cope up with it. So we came up with the idea of hybrid quantum classical systems. This is where the idea of quantum machine learning comes in. So this was the discussion around the variational methods, and in which we focused on the different areas, understanding of a variational quantum classifier, how quantum kernel methods can be harnessed, and uh, the area that all of this belongs to, that is quantum neural network. So uh, instead of using weights and biases as parameters, now we are focused on using theta, that is the rotation angles that come up, that is Rx, Ry, Rz gates that are coming up from the idea of poly XYZ gates only, that they are becoming rotation gates. So how these gates and their uh, angles now will act like a parameter. So this was the discussion around variational methods. Now today we ask the practical question that faculties and students really want answered. And that question itself is, what can these machines actually do right now? We discussed the idea that is okay, variational methods and all, but everything till this point we have seen is with respect to that, okay, uh, we can simulate something, we can simulate many ideas, but on real hardware, what exactly can be done, and what are the challenges that we might see with respect to this understanding of how uh, any algorithm will run, either when we run it on a simulator and when we run it on hardware, a real hardware. So with all this, it is also important to understand that how this is specifically for faculties, that how do you take all of this back to your own classroom, so as to inspire your students, that how this is one set of one new field that is like emerging very rapidly, and we are seeing too many changes day by day, and how everyone can cope up with it, come to understanding of the basic fundamentals, and also connect the different other fields like AI, and uh, the idea around Gen AI, agentic AI, and cybersecurity, and many things like that. User-centric computing. So how this can be taken back to the classroom. So this is what we look forward to. Now, past 4 days we have built the toolkit, that, uh, with starting with the foundations itself, and today is like a kind of a payoff, that what you are taking with going away with. Now, yesterday's variational loop wasn't just for the idea of machine learning, as we specifically did, we discussed the quantum machine learning and all. Uh, Today, we will be watching those same loops solve some problems pertaining to chemistry, and some optimization problems. And these will be some real problems. We'll also cover the idea of quantum security, that what is the problem that can come up with the invention of quantum computers, how we should prepare for the imminent threat that can come up with this, and how this can we will spend real time on teaching this, because that's the whole point of the FDP, of an FDP. The So the goal isn't for you to leave just impress. It is for you to leave kind of able to explain, able to explain, run, and teach this to your students. Now, let us see today's agenda. So, part A is all about the reality of today's hardware. So, whatever we have discussed till this point has been from a kind of a software point of view, that how any algorithm will run, how it is going to be simulated and everything. But we haven't seen any real case of hardware, and it is a little bit tedious also. You will get to know that yeah, even making a simple, you can say, IBM Qiskit or IBM login, that is platform login, is somewhat sometimes little bit time taking. So reality of today's hardware, that what NISC actually means. Then part B caches in the variational loop, as the idea of VQE and QAOA props up. So VQE, that is variational quantum eigensolver, as we were discussing. QAOA is the quantum approximate optimization algorithm. Then part C is our security, that what exactly goes on with respect to the Shor's algorithm, the Shor's threat, what happens in post-quantum cryptography, and what we mean by the idea of quantum key distribution and the BB84 algorithm, and many things like that. And we'll see some lab with respect to the NISC idea, the VQE, QAOA, and BB84 protocol. Then last part, that is the teaching payoff and the wrap up, and how notice how it moves from the idea of hardware. We start with hardware, then it goes towards applications, the variational applications. Then what are the implications, and then how this can be infused in your own classroom. So that last part is where this becomes yours. Now, before proceeding, we'll start with the NISCAR and all. I have tried to keep today's session uh, a little bit less in the terms of just the theoretical understanding and all. I would like to have a Q&A session through chat only, so that everyone can get their can ask their questions. Possibly we'll do that post 4:30 p.m. so that everyone can ask their questions, because uh, everyone can understand this, can go through different resources, whether they are YouTube resources or anything like that. But it makes a little bit more conducive, more rounded when we have some Q&A. So I would like everyone, I invite everyone post 4:30 probably to, or if we finish before that, then also it is okay, so that we can have a good amount of questions. Uh, I really like that everyone asked a good amount of question on day one, but post that it has been a kind of a drought. So yeah, I invite everyone again to like ask the questions around whatever we have discussed from the past 5 days, not just today, from the past 5 days, and what the future holds in for us in next. Now, let us start. See what exactly we are moving on with. So let's be clear-eyed about the machines we currently have, and these machines are known as what? We have been reiterating this word again and again. It is noisy intermediate scale quantum. And every word in here actually matters. First of all, what is intermediate scale? So in here, the understanding is that for intermediate scale, we are uh, trying to handle tens to a few hundred qubits. We are saying that tens to few hundred qubits. We are in that phase that we can handle these much qubits only. So in case if there is some problem, real life problem that goes beyond this, it will become certain. It will become a little problematic to handle these kind of systems. So we are focusing on a few hundred qubits right now. Then the part around noisy. So what exactly we mean by noisy is there is no full error correction current at this point. So gates and the readouts that we have, that is we do, they make mistakes. And when we uh, go about building deeper circuits, they might degrade. So that's a kind of a bigger problem that we see with respect to the system being noisy. And this single fact drives everything. It is why we favor shallow variational algorithms, as we were discussing yesterday. That why variational algorithms fit in this category of NIST, because they are shallow. Circuits here are shallow, and the honest framing that we can pass on to the students is that this era is all about useful experimentation. We are what saying it is specifically useful experimentation and not yet broad practical advantage. So we are in an experimental phase where we are trying to see that what exactly is working out for us and what is not. So how uh, based on what exactly is working out for us, we can do some optimization around it and come to a conclusion that how this hybrid systems, how we can proceed with respect to these hybrid systems. So that is why we are focusing on shallow variational noise tolerant algorithms right now. Then a quick tour about the quantum hardware platforms, that what exactly is happening right now, because many of you might be curious that what do these actually look like, and how we are using different techniques, hardware techniques in various, we can say, ways. So, a company might be using some X technique, maybe superconducting qubits, whereas some other company is using maybe trap dance and anything like that. So depending on the different technologies that we have, uh, there is no single winner. So several technologies are competing right now, and the superconducting chip, as it is used by the IBM and Google, they have a very pretty fast gates. So this is where IBM and Google come in to like chip in with their ideas. Whereas trapped ion, it is being used by the IonQ and Quantinum. They are very famous, you can say, organizations. They might be somewhat slower, but they are quite precise. So we can say that they are exquisitely precise, and every qubit is able to walk to every other. This is what uh, the special idea that trap dance come in with. So if you are understanding this, that step in a way, every technology is having some or other advantage, whereas some challenges will also be there, some limitations will also be there. So if trap dance are good at all-to-all coupling, superconducting are just very good at the fast gates, and they are specifically chip-based. Now, in comparison, the photonic and neutral atom approaches, they actually chase room temperature. And this is very important point because I think recently there was, I think, a news clipping from the Quantum Valley that is situated in Amravati, Andhra Pradesh. So uh, we were we had like reached to the minus temperature that we needed, and almost very close to that. I think minus 273 degrees Celsius. It is something like this. It's used to make the uh, qubits in a better shape, in a better state. And this idea of having room temperature or highly scalable approaches is very, very important in making this operation, we can say, to actually make this massive scale, and keeping this operational from different point of view. So the reassuring takeaway is that the circuit model that we learned this week, that we focused on just the circuit model. We started with the idea of different models, whether it is the first one was a circuit model, that is a gate based model, or measurement based model, or the photonic photonic based model, whether it is adiabatic computing, or quantum annealing, or topological computing, or regenerative computing. That is a very emerging model, and it is actually it will focusing on that. The regenerative computing will try to replace every other model, so that as it is working on some regenerative principles. So every model that we have discussed, specifically the circuit model, runs on all of them. And this is the beauty of the circuit model, that we are not locked on to just one vendor's physics. That okay, if we move towards trap dance, and we are not able to do something, I can say X thing, and in photonic we are not able to do something else. It is not like that. Circuit model is a kind of a universal model that is currently being used here. It is not a specifically universal model, but just like the von Neumann or the Turing machine, but as we say, that a universal machine, but uh, it is a primary model currently. Now, a very small demonstration through a game. I will like to show you a very small game for specifically showing you the idea that we were discussing about room temperature or highly scalable approaches, and the understanding of how heat actually you can say uh, decovers the system. So let me share my screen again. Yeah. So I hope everyone is able to see this game. This is a qubit game, and why it is important, because I just understanding the basic theory around that what is happening with respect to the room temperature and high fidelity and everything is not just enough. So this game has been built to understand that how a quantum computer is built, one qubit at a time. And some time back, before we were starting the FDP, I had played this game specifically. Tried to find something like this, and I was like at a very good. I had come up to a good. Uh, I think spent 30 minutes, or you can say an hour or so, more than that. So there were many things coming up in that scenario. So okay, this is coming. Okay. So I had like built up this, so it is perfectly coming up like that. It is not starting from zero. So what exactly is this scenario right now is these bodies, as you see, that are like you can see it, the resemble like a living entity. They are uh, qubits, and this particular you can say red body is a heat uh, material, and if this heat goes nearby any of the qubits, uh, these qubits will decoher. That is, they will need to start going into superposition and then the entanglement with the other qubits from right from the start. So uh, the idea in here that we have to just change their direction and many things like that. And if you see the setup, we have in here the coolant. So these qubits actually, when they are running, they will be producing the values, the information, and this information is actually giving us the ability to have some upgrades. If you see this, we have this signaling mechanism also here, where there was some calibration needed, and through this calibration we have built up some more advances. So if you see in here, we can do some qubit storage, that is expert qubit storage. That is, maximum qubits will be increased to 265. Right now it is 85 from the last update that I had done. That if you see this, the count is 50 out of 85, and the speed with which they are spawning is 1.2 seconds, and the max information that they can contain. This is the major idea, that every qubit right now, if you are seeing, is having some maximum capacity, and the production speed is something like this. So everything in here goes on. When we see, if you see this, uh, it will be showing you the quantum encyclopedia, and very good idea, very good way to like understand what exactly is going on through a game. You are understanding it is okay with every it should be used, can be used by anyone, whether you are faculty or a student, because this is giving us a basic understanding of what exactly is happening. And uh, this whole document will unlock as you go along the modules. So right now, if you see this, we have qubits, the idea of qubits, how they store information, what's with the idea of measuring the information. So that as you see, so that when we clicked on it, it is now measuring the information. This is what exactly this means. So right, like this, when we have multiple qubits, how this can actually lead to this entanglement, that is this. So you will not need to press every other qubit to like get the information. In entanglement, you will just click on one qubit and you will get the whole information at one go. So the information, the currency in here is information. Like I have currently 729 information, and I if I just get to any of these milestones, that is these different milestones, I will be able to open this particular. uh, uh, speed up, or you can say the kind of any kind of a technique. So cooling the qubits, this is if you see that this is heat material, and I need this needs production from the heat. So cooling the heats require that we have some coolant and many things like that. So this is a kind of a way that how quantum computers real hardware actually works. And if you see this, there are some things that are still blanked out. That is, we haven't reached the particular state where we might be able to see that. So if you see this, we have some ideas around expert qubit manufacturing, exact information capacity, qubit speed, and many things like that. And this goes on and on. That how analog signals can be used, so we can like talk to qubits in that way, and many things have not been still uh, unlocked. So this is the idea. Let me show you if I can like change its direction and show you that, okay, uh, how a qubit will, if you see this, what happened, the this qubit, this particular qubit, and actually uh, got decovered. And if you see this, many uh, uh, messages are coming up that I am entangled, or measure me, or that I am full, and many things like that. If you see, if I do this, I am able to get this information, and this currency information is piling up. And this is the exact basic understanding of what is this game is about. So if just for a more second, if we see, if you see that we have a coolant that is already there. If the heat attack is sudden, if many heat particles attack, we can apply this coolant so that the whole system actually is behaving. Now if you see this, this has decovered, although this was very in very good shape. It was having a whole 20 bits of information, but it decovered because of this heat material. So we can apply this coolant and many things like that, so to get an understanding of what exactly is how this will get cooled. Now if we just minimize it a little bit more, you see this is what the architecture, and that is the real hardware. If we go to a lab, uh, a real lab, it will look like. And the coherence currently how it is there, what's the heat measure, the information confidence, the speed, and all is everything being shown in here. So this is what the idea is all around these. Just a second. Yeah. So this is what the idea around this qubits and is all about. So this might seem a simple game itself, but it's not a game. It is an way to make anyone aware about what exactly happens in the background with respect to the qubits and all, that how we actually see the understanding of what these different quantum hardware platforms is all about. Now there are two specific ideas around mitigation and the correction, and there this is where the distinction between them, uh, people constantly muddle around. So let's try to understand. We do not want to confuse them. So mitigation is what we do today. That is, we are doing clever post processing that reduces the bias in noisy results, and it is quite cheap, it's partial, and it needs no extra qubits. So this is what we are doing with respect to mitigation. That is today what we need to do. Correction is all about the future, that if we encode one perfect logical qubit inside many physical ones. So how this idea can be actually implemented? It genuinely removes the errors, but it is enormously expensive in qubits. So today we actually live with the idea of noise and mitigate, and uh, from a late from you can say long context, from a later point of view, what we are focusing on is that fault tolerance is what finally uh, unlocks the era one algorithms like Shore at full scale. So we are still waiting for that. We are not still capable of start uh, at a scale to handle that. So a very important point of how the error is handled currently and what future holds in for us. Then, before moving on to the specific applications, just recall the variational loop that we discussed. Uh, the one idea that they all share is the loop that we discussed from yesterday. Uh, that started with running a parameterized circuit, and as we run this parameterized circuit, we measure a cost with respect to that, and then we let a classical optimizer nudge the angles or optimize the do some optimization update, whether it is a gradient free technique or gradient based technique, no issues. And then this is repeated until and unless we converge, we come to a point of convergence. So the important idea that we have, important kind of a punchline for today, what we focus on is that the only the cost changes. That is, we make the cost a molecule's energy, and from that we get the VQE, that is variational quantum eigensolver. If we make the cost as an optimization objective, we might get QAOA, that is quantum approximate optimization algorithm. What same for if we make the cost kind of a uh, way, in a way that how new drugs can be discovered, how what drug discovery can be done. So it will be specifically used for that particular optimization objective. The objective will change accordingly. So the machinery is same, but the applications are different. That there are two different applications, and the same cautions from day four still apply. That how to handle barren plateaus and the short cost, that the different shots that we see in our system in. So specifically keep the slide keep coming back to the slide for the next two applications that we are going to see, that is with respect to the chemistry and the optimization. Now, the first application. Uh, the first application with respect to the chemistry is that yesterday's loop with the cost, it is kind of a it is set to energy, that we whatever we have seen in the terms of yesterday's loop, we set it with the cost, and this is where we get the ground state energy of a molecule. And the idea of Hamiltonians, the different Hamiltonians, how this actually uh, is harnessed. So we minimize the expectation value of the molecule's Hamiltonian over the angles, and the minimum we find, it actually approximates the true ground state energy. So as you might be aware that a molecule has different you can say energy states, ground state and an excited state. So what we actually are focused in here is to uh, find out the ground state energy of a molecule, and how this can be, the cost around it can be minimized. So this is what the focus is with respect to the idea of quantum chemistry. So The question should be that why exactly are we interested in doing this on a quantum computer at all? Because what benefit we are going to get from this? So the idea is that the molecular states, they live in an exponentially large space, and this is exactly what classical machines choke on. And we had seen one example, one specific example on day one, that was of caffeine example. This example certainly warned us that the idea around having to simulate a caffeine atom that has only 24 atoms, or a caffeine molecule specifically saying, let us say that, so it has a 24 atoms. So how it is becoming cumbersome to handle it, because uh, we are not able to simulate that caffeine atom in from through a classical computer. So this is where the idea of a quantum computer comes in, that we have to handle these exponentially large spaces. And this is chemistry. This is, we can say, we can particularly use in chemistry. It can also be used in different materials or drug discovery. Uh, and this is kind of arguably the most natural fit for near-term quantum computing. So this is a kind of a leading NISC application. That's the bottom line with the idea of how quantum chemistry is evolving. Then we have the second application, that is with having same loop, but uh, the cost parameter is now different, and it is a kind of a new cost. So QAOA actually tackles combinatorial optimization, uh, and uh, there are different, you can say, examples like max cut problem, where we split a graph's nodes into two groups to cut as many edges as possible. So this is what we actually focus on. And the structure that we have with respect to this problem is that the circuit alternates between two different ideas, two different layers, and those are the cost and the mixer layers. And this actually contains this is consumed in the idea of this Hamiltonian only and nothing else. So these layers, the cost and the mixer layers, are tuned by the variational loop itself, and then we simply just sample it. That is the most frequent bit string that we will be getting from this partitioning. That is, when we partition the graph, that will be our candidate solution. So a quick note about what exactly is goes on with the idea of combinatorial optimization is like, it is a branch of mathematical optimization only, and we are focused on finding the best possible object, or the best possible, you can say, sequence of actions, uh, and this is found out from a finite, or you can say discrete set of options, that we have some finite or discrete set. This is where we can find this particular candidate solution, because as the number of possible solutions, it grows exponentially. uh, Doing exhaustive search is usually impossible, because if we say that, okay, if state space is growing exponentially, if we just go on about searching, that doing some exhaustive search, it will not end any time. So the idea around combinatorial optimization is to focus on the best possible set of actions in a finite or a discrete, you can say, set. So uh, specifically for a max cut, we find the most frequent bit string uh, through the alternating cost and mixer layers. And this is actually being tuned using the variational loop itself. So in variational loop, if you remember correctly, that the classical optimization that actually tunes to the parameter tuning, everything with regards to that. And what is that parameter? The theta. So this is what is done with respect to the idea of max cut in optimization. So the use cases are like everywhere business lives. Actually, right now it is with respect to the logistics, scheduling, and the finance, and these are very promising ideas, but not yet proven to beat the best classical methods. They're still in experimental phase, as as we had established. There is no direct proven quantum advantage, but uh, there is a chance, there is a ray of hope that these problems, we will be able to solve them more efficiently than some other techniques. Then comes up the one of the flip sides of uh, the idea of using quantum computing. Uh, so far, quantum computing has been a kind of a tool. Uh, Here, it is becoming a threat. And why so? Because the Shor's algorithm that we discussed on day three, uh, as you remember, it factors large numbers efficiently. So factoring a small number like 15 can be factored into 3, it cross 5, that is perfectly okay. But factoring a 10-digit number or a 12-digit number or a 20-digit number, it becomes quite tedious for a classical computer. But Shor's algorithm is able to factor the large numbers efficiently. The basic idea is that. And this whole idea actually breaks the RSA algorithm that we have, that every device currently runs on. Uh, uh, I think it is seen as Rivest, Shamir, and Alderman. Three guys came together in 1976 to uh, propose this algorithm, build this algorithm or protocol. You can say. So this RSA and the ECC, that is the elliptic curve cryptography, that is used. They are the backbone of today's internet security, and through Shor's algorithm, they are like getting thwarted. So it becomes somewhat problematic. So the catch today is that, and it is a very precise idea in here, that it needs a large error corrected machine, but we don't have that yet. So Shor's algorithm will need this kind of machinery to have to break the RSA and ECC. So it's a kind of a future threat. We can't be uh, just too reliant on the idea that okay, this kind of computer will not be there in future, or uh, we will not be seeing any high-end quantum computer that or fully fault-tolerant quantum computing will not be there in next 5 to 10 years. So that will be a kind of uh, uh, a wrong way to go about. We might see some fault tolerant quantum computers. It might be a little late, but yeah, the possibility is quite clear that we are going to see it in our lifetime only. So as it is a future threat, and this is what I specifically told you about in the first day itself, that this is what currently we say it as that harvest now and decrypt later. That this makes it urgent today. uh, because adversaries can store encrypted data now. A intruder who wants to maybe see who is like has got hold of your data, they can just keep it today, and they can crack it once the hardware arrives. So that is why the response has to begin before the threat is actually real. So that is why the response should begin now. And this is not just you can say a kind of a mythical threat. It is not it's not like that. It is a real threat that is being worked. Many organizations are working on this, at how this can be uh, handled. Then here comes the practical near-term defense, and this is available today. That is the classical defense that we see, and that comes under the idea of this post-quantum cryptography, and it's reassuringly down to earth. So, post-quantum cryptography is actually classical cryptography that is built on math problems we believe even quantum computers can't crack. Okay. Uh, and there are some certain lattice problems. So, a quick idea uh, about what exactly is the understanding of these methods. Classical computing, the best security mechanism that we have currently in classical computing is RSA technique. And if you understand the basic idea of it, you'll see that behind RSA algorithm is a mathematical foundation, a mathematical idea that we are able to handle our public and private keys, how we are stacking them up, and what's the symmetric and asymmetric cryptography, and many things like that. So the solution, so in classical computing, the solution is mathematical. If we see that distinction between them, whereas in quantum computing, the idea is that in we are seeing the solution from a physics point of view. It is not just a new kind of a mathematics. We are seeing a new kind of wave that is coming from a physics background. That is, all the ideas that we have discussed uh, pertaining to quantum computing are coming from the idea that started with the invention of the coin termed the term that was coined in 1925, that is quantum mechanics. So everything that we have seen, whether it is a qubit, uh, superposition, interference, measurement, entanglement, Hilbert space, uh, uh, anything with respect to this idea around quantum computing is coming from this quantum mechanics background understanding only. So sometimes it can be said that we are actually trying to compete the physics versus mathematics, that is mathematics from the classical point of view, and physics, that is physics driven solutions from a quantum computing point of view. But the goal is to we do not want we are not focusing on uh, you can say a kind of a brawl, that we, okay, physics is good or mathematics is good. So there has been like this has been going for past some time, that okay, that physics is the real science. Some say mathematics is the real science, and some say biology is the real science. Some might say chemistry is the real science. So this is not what we want, what we are intending to do. What we intend to focus on is that how we can uh, harness all of these sciences into one coherent model where we are secure from us as humans that are currently the uh, most developed, you can say, species, how they can be secure from any kind of you can say intrusion. This is what the focus is currently right now. So as we were discussing that how post quantum cryptography is can be built, it is being built as we discussed that it is being built on math problems we are believing that even quantum computers won't be able to crack. And again, if you see the understanding that whenever we are discussing about classical cryptography, it is the idea that the idea we come up with is the math problems that we are uh, designing so complex math problems that the quantum computers won't be able to crack that. Whereas there is flip side in the other domain with respect to quantum computing. We are focusing on physics oriented quantum solutions that are actually defining some new kind of properties. So the beautiful part is that it runs this PQC, the idea it runs on completely ordinary hardware. We do not need a specialized quantum hardware. That is very reassuring. So no quantum hardware is needed to defend against one. That is, in opposition we do not need we have uh, uh, a classical hardware only, and if we have a quantum hardware in its you can say opposition, we do not need to change our quantum classical hardware with PQC to that particular to some new quantum hardware. So, and the idea is that this isn't just theoretical. It's not just that we are just blabbering some theoretical ideas. It is there have been some standardizations, and the list that came up with. So it's the, I think, National Institute of Standards and Technology. They came up with the PQC schemes in 2024. You can, I think, see that over Google search only. That in 2024 they came up with the first schemes, and the migration is already underway in this regard. So this is specifically for the faculties. If your student asks that what do we actually do about the quantum threat right now, then this is the answer. This is the uh, best available practical near-term fix. We are not discussing about the not concerned right about the harvest not decrypt later idea. We are saying that okay, PQC can that is post quantum cryptography and the NIST standardizations uh, are the answer to the current quantum threats that we are seeing. So with this, we also have another kind of approach. And if you see this specifically, that is the first line, security from physics rather than mathematics. And this is very, very important. And that is why I try to give you a prelude of what exactly we are going to discuss next. Uh, and I would like to discuss this QKD and BB84. Maybe I'll try to see one or two articles, or maybe some particular ideas from where this can be, how this is shaping up. So this is a radically different approach where security from physics is at the help instead of mathematics. And the protocol, that is BB84, what actually goes on around it is that Alice and Bob, let us say they are two uh, persons who want to communicate, and uh, Alice and Bob want to exchange qubits in randomly chosen basis, and they sift out a shared secret key. So why is it secure? And the idea why this exactly secure is coming from the two ideas that we discussed on day two. Specifically, first one was the no cloning theorem, and I'm hoping now everyone is maybe connecting the dots. Why there was so detailed discussion on no cloning theorem on day one after I think when we were completing the proceedings on day one, I just discussed briefly, and then on day two we discussed in very detail that what exactly uh, we mean by the idea of no cloning theorem. That how when Alice and Bob are communicating, they are exchanging qubits, how that communication or that channel will break or will decoher if anyone wants to uh, like try to sneaks in. So that's the first idea. And the measurement disturbance, that you can't uh, like copy paste. First of all, that is from no cloning, the copy paste the a random quantum state, and you the disturbance will be there with respect to the measurement. So this is why the idea of this BB84 protocol is very important. And the security of BB84, uh, this actually relies on how the qubits are transmitted. That is, they are usually mapped into the polarization states of single photons to securely generate shared random key, and this random key is actually will be used for encrypted communication, and it operates through some of the steps. What are these steps? Is that we start with the idea of state preparation. That is, Alice is the sender, so she will be preparing the states. So this state preparation is the same idea that we were discussing in QML, and uh, the basic idea is that state preparation is a general idea. In QML, we will specifically seeing some application that how it can be done. So state preparation, in a state preparation, the let me show you in here. I think we can do that. We have the liberty of time. Yeah, because this BB84 is very important. So I hope I'm hoping that this uh, you can understand this, because this the idea of quantum key distribution, how key distribution actually happens. So many of you might be from a cryptography background, and they know that how important RSA has been to us. Currently it is it is very useful, and I think we are completing 50 years for the RSA algorithm this year itself. That is, it was started in 1976. So very important algorithm. So BB84, how BB84 and QKT will have a different approach. So the first idea we say is of state preparation, that is being done by Alice, as she is the sender. And what exactly she is doing is Alice is preparing a stream of photons. This is a stream of photons, and uh, it will encode each bit of her key as either a 0 or a 1. So whatever key she has, it will be encoded in the terms of 0 and 1 only, just like we do in with respect to the ideas that are used in computer networks. The basic, I think, course that we have, that how um, uh, various techniques can be used to do some encryption methods and more, or maybe specifically for a cryptography course, we have a more detailed idea of how that is done actually. And for each photon, that for each the stream of photons, the each photon, she randomly chooses one of the two polarization bases. That is how these bases and all are discussed. We are not going into that. So these bases are chosen by the Alice. And we say choose one of the two polarization bases. So specifically, what are these bases? Just we are just writing the names. One is rectilinear and diagonal. So these are two different types of bases where in rectilinear, zero will be encoded as vertical and one is encoded as horizontal, whereas in diagonal, zero is encoded as diagonal, that is 45 degree, and one is encoded as anti-diagonal, that is minus 45 degree. Now, this is the first step in the PV84 protocol. Second step is to have the measurement. That is, Bob will be measuring it. So what specifically goes around with this idea is that the receiver, that is the Bob, uh, it receives the photons and it randomly measures the polarization of each base using one of the two bases that they have shared. And uh, these one of the bases that is it has, that whether it is a rectilinear base or a diagonal base, it will be measuring that. Now, I hope you understand that if the bases match, it means Alice has connected with the Bob. This is the basic idea. But if Alice has uh, like sent some base and another person, not Bob, maybe Eve, is trying to intrude, then those bases will not match. It means the connection will not be made, or you can say it'll recover. So that is where the whole security part actually comes in. So last part that we have with respect to this is sifting. It is not shifting, it is sifting. Sifting. And what this means actually is Alice and Bob now communicate over a normal classical, or you can say public, not classical, it over a normal public unsecured channel. And they compare the bases they used for each photon. So they will be discarding all the instances where their bases did not match, and the remaining results, the remaining matching results, form the sifted key. This is what known as sifted key, where bases match. So this is the basic idea of BB84 protocol. Now, how eavesdroppers are detected? Uh, Specifically, measuring a quantum particle in the wrong basis disturbs its state. So any eavesdropper, that is typically seen as EVE, who tries to like intercept that any system, and uh, it will actually uh, leave a detectable footprint of when Eve tries to read the photons. So Alice and Bob like can spot Eve by publicly comparing a random subset of their sifted keys, these sifted keys. And if the error rate exceeds an agreed upon threshold, they will know that some eavesdropper was present, and they immediately abort the transmission and they will start over. So this is what goes on with respect to the BB84 protocol. Now, as we were focusing on that, this the practical implementation is that BB84 is grounded in these physical principles, physical specific principles, rather than just a mathematical complexity. And what is the physical principle that is coming in here? If you understand this, that the polarization of the the photons, that stream of photons are going from one person, that is the sender, to the receiver, instead of having the uh, complex mathematics like RSA uses the Euler-Tottian function, where we specifically use the Euler's function, Tottian function, to get the understanding of the different prime factors. We are specifically using some physical principles like the stream of photons to do the encoding and check our results with respect to the two different polarization bases. And this is the basic idea around BB84 protocol. So I hope everyone has like at least understood the basic idea of what exactly is going on. More can be discussed in detail, or you can say you can go about it at your end. Now, uh, as we discuss, said that whenever Eve will try to look, it will be raising some error rate, and this error rate needs to be checked that whether it is going before a threshold or not. So the trade-off is important in here, and what is that? That it needs special hardware and channels, so it complements the idea of PQC rather than just replacing it. So we'll try to see this in the hands-on lab shortly, that what exactly is happening. So it is not actually replacing PQC, it is just complementing it. Now, let us zoom out to where the real action is actually. So chemistry and materials, where are they used? So variational quantum eigensolver is it can be used for molecules and batteries, and this is the most natural fit for it. Whereas the idea of optimization, specifically through the quantum approximate optimization algorithm, is being used in the routing problems. Uh, so the different routing problems, that how again coming back to the networks, computer networks, how a packet will be uh, routed through different channels, and what mechanism it will use, uh, what different ways we can route a particular packet. uh, this becomes very important. uh, so the idea of routing and the scheduling problem, that how uh, different ways of scheduling, any scheduling problems can be handled, whether uh, uh, it is is short, small scheduling, or any bigger scheduling problem, that how it can be handled. And also the portfolio optimization, that finding the anomalies, how anomaly detection can be there in financial transactions, uh, how to diversify the portfolio, just like if I am trying to invest maybe some 10 lakh rupees, I will not like to invest in just one, you can say, scheme, or one way that it gives me a kind of a 4% of interest, 4% of profits, we can say steadily. I would like to maybe diversify my portfolio in such a way that I am uh, I am diverting my funds to some uh, secure some secure methods also, as well as some uh, methods that are quick but um, in a long term they are unsecure. So the idea of this routing, scheduling, and portfolios is the broad, you can say, broadest uh, idea with respect to commercial interest. And the idea of machine learning also comes in that uh, we discussed the understanding of how machine learning can be used to, like, quantum machine learning can be used to have feature maps, quantum feature maps, and the quantum kernels. So this actually rounds it out for the understanding of where the application landscape is currently. Uh, but an honest understanding is that this is all active research. It is not that we have like found every uh, uh, answer to everything. It's still in active research area, and a clear general advantage is is still to be demonstrated. So we are framing these problems as promising directions that your students can work in. They can actually take baby steps and not just solve the whole problem. At least they can like, start with the understanding of what is going on in this area, in these particular I can say fields. Now, before going to the Q&A and all, and other things, we will see some lab session for this. That first of all, we will be running an ideal circuit versus a noisy one, and we'll watch that how noise appears in that particular circuit. That when we will be introducing some uh, random noise in the our circuit. So that's the first part that we will be focusing on. Then the architectures around VQE and QAOA. It will be literally reusing the yesterday's loop. Then move on to the idea of PB84 protocol, where we will see secure versus eavesdropped uh, idea. And um, I there is one thing I am like kind of not happy with, that I tried to run the circuit on a real quantum hardware, but uh, currently the IBM hardware, it requires a credit card, and I tried to verify it many a times, but it is not verifying, and I have only one credit card. So that's a shame a little bit. But yeah, I'll show you that the platform, the IBM platform, cloud platform, and you can just verify yourself, and through this credit card and all. And then you can, if you want, you can also run it the problems in a real IBM hardware uh, from these notebooks itself. So I have like uh, put out an optional way to see that, but it needs a verification from the IBM cloud services. So we will be having this basic understanding of building and then running and repeating the whole idea itself, and then how to read our specific results. So let us now move towards these hands-on lab, and everything around it is like same thing, nothing else. Specifically, if I would like to discuss one thing before that, is like how to teach quantum computing. Everyone, every faculty is a capability, you can say, teacher. They are excellent in their areas, in their areas. So I'm not here to like give sermons of how to actually teach. It is about that how to shape up this whole idea, that this actually makes the whole the whole FDP very interesting, on how to turn this week that we have discussed into your courses that can be incorporated in the colleges and the universities you are currently. So a few hard-won principles. We start with the visual representation of superposition, interference, and entanglement before we move towards any heavy math. Uh, and we tried to see every everything in here with from a visualization point of view, whether it was through Glossosphere or the IBM Quantum Composer. So that is why I preferred to discuss in IBM Quantum Composer, so that you can understand the drag and drop instead of just going directly into the code and not understanding anything. So we should start with that. You can start with that, and that's how we opened on, you can say, day one, on day one also, and it works quite easily. Then uh, get the students onto hands-on idea that we have free Qiskit and IBM Quantum, and they can run real circuits in one in starting, we can say, some a few weeks in itself. Then you need to follow the arc we have used all week. That first we started with the concept, the basic concept, then how the gates actually shape up. That is the idea of uh, single qubit and multiple qubits, what exactly is going on with respect to that. Then the different algorithms, the proof of concept algorithms, and the algorithms that actually matter, the application based algorithms, not just the toy problems. And the variational computing, that is we move towards the quantum computing and many other things. Sorry, quantum machine learning and many other things. So how variational computing can come up, can be of help. And this actually completes the whole arc of this FDP, that what we have been building in for the last week. So where there is one important aspect that uh, you have to focus on showing them that what's the promise and what are exactly the limitations. So we are not just we are just, building understanding, or not just the hype that okay, quantum computing can do many things, but what exactly it is doing, and we are not able to understand that. So yeah, so this is where the idea of incorporating the quantum computing into your courses can come in, and this exactly is the whole gist of this FDP, I guess. Now let's move towards the idea of hands-on, as we were seeing. Just a second. Now, in here, what exactly are we seeing is we will be focusing on first of a setup, basic setup, nothing else. And this has been like the same case for the on the 5 days for or the 5 sessions. Then the MISC reality, that is the ideal versus not noisy hardware. And if you see specifically the difference that will be coming up, we'll go through this step by step. Then the ground state energy of the hydrogen molecule, and cost is specifically here equal to energy. I am not expecting everyone to like just um, uh, apply this right away. It is not possible, but at least understand what exactly is happening with respect to this graph, that how energy state and iterations, and the number of iterations, how it is mapping up actually. Then the idea of max cut optimization, that what's the cost in here, that is a problem objective, and what's the best partition that is coming up with respect to this, that string, that bit string, the bit string is coming up to be 0101. So again, do not we do not want to go directly just deep dive into it. We just need to focus on what exactly is being done in here. The sharing a secret key when there is no eavesdropper. So what will the shifted key, and that it means the channel is secure right now. When the eavesdropper is detectable, it means then what exactly will happen. And this the optional run that can be done on a IBM quantum processor. Will need to just um, uh, try to do this on your end, because I am literally not able to like run this because of some technical faults I am possibly. So you just need to change in here true, and it will actually be running on quantum, you can say hardware. But be aware, you get I think $300 of credits as uh, starting gift from IBM for a month, I think. But it you have to use it judiciously, because the cloud platforms, AWS, whether it is AWS, Azure, or Google Cloud, or any IBM Cloud, anything, they rack up quite a bill if left undone, you can say on. So this is one idea, and the reading the results. Okay, let's start step by step of what exactly is going on with this. So setup is simple. We have this basic same setup, nothing different in here. Now coming to the NISC reality. Uh, Before this, if yeah, we will be starting with the Q&A and many things like this. I would like to answer your questions. uh, if you have any question, do send them in chat itself, and I will, after this discussion, we will try to discuss that. Okay, so in this reality, what exactly is happening in here is that we are focusing on the goal in here is to create a Bell state, and we need to compare the ideal quantum computer, what happens in an ideal quantum computer, and what happens in a noisy quantum computer. So first of all, we are making a Bell state with respect to the two qubits and the two classical bits. uh, so this is what the idea is, and if you see this, we are applying Hadamard, then the C naught gate, and we are then measuring it. That's the first step in this idea. So with Hadamard, it will be going to superposition, then it will be entangled, and it will create entanglement, and then both qubits, we measure them. So this is the basic idea with respect to the first point in here. Then very specifically important, this idea, that is noise model. What is this telling us? That we are creating artificial noise, and this imitates today's real quantum hardware. So this is the first point that is important now in here. Next, if you see that depolarizing errors, what exactly is this referring to? Is that we add random errors after gates, for 1 qubit gates also and 2 qubit gates also. So real quantum computers, they are not perfect. This is what we are trying to imitate, that a kind of a real quantum computer. This is just a simulation currently, but we are trying to imitate a real quantum computer from the point of view, from the context that we can, are we able to, we are trying to add some noise to it, so that it actually gives a effect of a kind of a real quantum computer, that is a noisy hardware. Because in ideal hardware, that is there where there is no noise, it will be actually kind of a thing that is not currently possible. It is a utopian idea like that. So real quantum computers are not perfect, as we said. Every operation has a small chance of making a mistake. So this is the idea that is being used here. That is the depolarizing error. We are introducing some errors to 1 qubit, and that is 0.05 in that sense, and 0.10 in the terms of to the 2 qubit gates. Then we are uh, uh, running this on a perfect simulator. That is the ideal part. We are transpiling the circuit for 2000 shots. We are running the this on a perfect simulator, and the expected output will be 0 0 and 1 1. This is the expected output, and this, if you remember from the Bell state, in the Bell state, what output we used to get for this particular Bell state, it was 0 0 and 1 1 only. And specifically we are using 2000 shots, so it will be giving us something like that. But is now see, for a noisy you can say system, when we would run it on a from this noise filters, you can say hardware, it will now give the probabilities of some other states also, and they will be small, but they will be there. So if you see, 0 0 is present 953 times, 1 1 is present 959 times, but 1 0 and 0 1, that is not a possibility actually. uh, as we saw in when running the entanglement and the other circuits on day two, that these were not coming up, but in that was from a simulator point of view, that was idealistic. Right now this is not idealistic, this is a noise filled, okay, or you can say noise mixed hardware. So that is why the main takeaway that we have from here is that today's quantum computers are called NISQ devices because they are noisy. Even if our algorithm is correct, hardware errors introduce wrong results, and this is wrong actually. If you do this mathematically also, as we discussed and we did, that we will be getting 0 0 and 1 1 only for this particular circuit, but this is not the case with respect to the noisy hardware. So very important idea that how ideal versus noisy hardware actually work around. Now, moving towards the variational quantum state eigensolver, this is like the probably the most important idea in here. Uh, that we start with the sparse Pauli matrix. That is, we are seeing for a hydrogen molecule, it is just defining how the hydrogen molecule is stacked up. So instead of storing the molecule directly, we are storing it as a kind a type in a type of a Hamiltonian. This is what the idea is. So Hamiltonian contains all the physics of the molecule. Then we are focused on this uh, getting us the true ground energy. So exact, we are focused on getting the true answer mathematically. So we calculate this true answer mathematically, and this gives us something to you can say compare against when we do something in a later step. Then we have the answers. So this answers will actually be creating a parameterized quantum circuit. And instead of solving the problem directly, we will be giving, we guess a quantum state. So parameters that are in here are given in the terms of 0 1 0, sorry, theta 1, theta 2, theta 3, and theta 4, like that. Okay. So with pertaining to this theta, that we will have different parameters. Then inside this NSAS, we are using some gates like RY and CX and the RY gate again. So RY is actually rotating the qubits, whereas CX is creating the entanglement. So these parameters can be changed repeatedly. So depending on, if you remember the basic idea that trainable layers, entangling layers, variational layers, and many things like that we were discussing. So entanglement, rotation is also there. So everything is being done inside this only. Then, sorry. So then the energy state. What exactly is this giving us? It will be computing the energy, that is the H state of the expected energy, or the expected energy that we have. This actually tells us the expected energy of this molecule. So the quantum computer, it measures the energy of our guess state. So whatever we have given in the terms of NSAS, it was what a guessed state. Then the minimize function will be just uh, uh, focusing on the classical optimizer that will be changing the parameter. So if you specifically say see in here, we are using the Kobaila method, that is a classical optimizer, that is a gradient free technique. So the flow becomes, what's the flow? That's the first idea. We guess the parameters, the quantum computer computes the energy. The classical computer, it changes the parameters using different parameter optimization techniques. Quantum computer computes again with respect to this change, with respect to these parameters being affected, and this is repeated until unless we reach a convergence point. And last point is the callback. That is, we call back this function, this lambda, and this later we this graph is drawn. Now, what this graph is actually telling us with respect to that, that is being seen in here, that is plotting the histogram. It is actually telling us that energy is decreasing. It shows energy, how energy is decreasing, and as iterations continue, our guess improves. So this is what the idea is around. And the eventually the guess will will go on to get better, then again better guess, and then will actually move to the ground state. So VQE is simply repeated guessing and improvement until the minimum energy is found. So this is the idea with respect to found that minimizing the molecular energy. What we are doing, we are guessing it and moving towards a better guess. Sorry. Then we have the idea of QAOA. It solves optimization problem. So first of all, we are having this edges. So we are creating a graph. So as it is giving us 0, 1, 1, 2, 2, 3, 3, 0. So it is actually a square that we have. So that's the our four node square graph where we are trying to see the most edges are cut or not. Then the cut value is actually will tell us that how many edges are cut. If two connect on what we exactly this means, if two connected nodes belong to different groups, that edge contributes one. So this is what the idea is around with respect to this edge cut. That is, two connected nodes, if they are belonging to different groups, we say that that edge contributes one to that particular idea. Now, the idea around this quantum circuit, we first build up the superposition, that is this equal superposition. That is every uh, qubit will start with the Hadamard gate and the range whatever we have depending on that. So we have specifically taken n equals to 4, that is n for 4 qubits. So every qubit will be uh, Hadamard will be applied onto every qubit. Then we have the this uh, every partition is actually explored simultaneously. So the RZZ gate, that is the cost layer, that is one of the part in the Hamiltonian problem that we were discussing, the basic idea that the cost layer and the mixture layer. So this is the cost layer. This will be marking good solutions. So this is what RZZ gate, that the rotation Z gate is giving us. Then the RX gate, it is the mixer layer. It actually allows the movement between different solutions. And then we are minimizing the whole state, that is this minimize. This is telling us that how classical optimizer changes until the cost becomes best. So the uh, uh, variables, that is alpha, gamma and beta, these specifically gamma and beta, how these are like updated until we get a good cost. So the final result will be the best partition, that is 0, 1, 0, 1, and this actually displays the best graph partitioning. So QAOA is using the same hybrid loop as VQE, and the only thing that changes in here is what we are trying to minimize. We are trying to get to a best possible string instead of the energy state. Then we have the baby 84 protocol, where we are trying to create a secure key where the Alice generates random bits, that is this random integers, and the idea around in here is that Alice will be selecting random bases. It chooses bases that Z or X, depending on what whether it is horizontal or vertical. And the Bob's random basis also, Bob is also choosing random bases. So this is basic understanding of how bases are being chosen. Then we get the understanding of this idea that how the bits are actually being encoded. So we encode the bit in this manner, and bit zero will start if we had bit 0, it will leave qubit. If we have bit 1, it will apply the x gate onto that. So that's the whole idea with respect to this encoding, bit encoding. Then the idea of choosing the basis. If x basis is chosen, that is the x or z. If x basis is chosen, then we are actually applying head on because it will be 1. So that's the whole idea in here. And Bob uses his own random basis, and based on that, the whole process goes on. So if bases match, then we will say that okay, this is called shifting. Bob has measured in his basis, and if the bases are matching, then we are saying that it is shifting. And if the bases are not matching, there is some error rate coming up, then it says we say that the calculation is being disagreed. So the communication is you can say secure, because the error rate is coming out to be 0%. So with this zero actually error rate means the channel is secure. So this is what the idea around shifted key, that is 14-bit key, and the error rate coming out, so channel is secure. Whereas if Eve is eavesdropping something, so there will be problem in here, that the error rate will now be changed with respect to that. That is, there with respect to no eavesdropper, there the error rate was 0.00. With eavesdropper, the error rate is coming out to be 0.25, and 0.25 actually means the intrusion has been detected and key discarded. So this was this range was decided by Bob and Alice itself. So in this undetectable one, the idea is that only measurements that are made in the same basis, they will be kept, and those will become the secret key. And With respect to the eavesdropper, so every Eve will intercept every qubit, and she will measure it, prepare a new qubit with respect to that, and it will she will send it onward. But she doesn't know the correct basis actually, so she might introduce error. So as we understand that the idea of quantum mechanics itself reveals the presence of an eavesdropper. So, unlike classical encryption, no mathematical attack is needed. Physics is actually detecting Eve. And lastly, the idea of running it on a quantum computer, real quantum processor. So normally everything has been running on a simulator till this point. This particular code is showing that how to execute on an actual IBM quantum computer. The steps that we have is to connect to IBM quantum, and then choose an available backend, and with regards to that, you can transpile the circuit and submit the job. And Then you will need to wait in queue, because if you are not waiting in the queue, then we will have to wait in the queue, because of the idea that this becomes many people are there that have uh, uh, have their job queued, and this will take some time. And after your number is there, you will receive real measurement results. So if this is set to false, you will not be able to see this. It will just uh, skip this part. Otherwise, the main idea is that the same quantum circuit can run on either a simulator or an actual quantum computer processor with almost no code changes. So very few changes, if there are any, they will be needed. Just like we have this Qiskit runtime service. This is being introduced, so it will use your saved account. So these are some things that are being used. So the final summary we have is that uh, we had seen the variational loop for VQE and QAOA, the physics for BB84, and this is the week in one session. This is what the basic idea of this whole FDP has been. And yeah, now if there are any questions, I would be happy to answer them. Any confusions, any questions, any uh, also there the resources, some other resources I will be sharing with the team, and you can see on it on uh, the LMS itself that what next after the FDP, because we just do not want to like go in from here with the empty hands. So uh, just a second. So this is like the week in one picture. If you see this, that we started with the qubits, the gates, the circuits, and the entanglement. This was the language from day one and two. We specifically uh, had seen algorithms, the source of speed ups on day three. On day four, we focused on the operational circuits and QML, and this is the basic turnaround for NISC idea. And today we try to see some real hardware. What exactly we try to simulate it, the idea of real hardware, uh, that what exactly is done, applications, the security, and how to take it forward. So that's the basic understanding of the week, the whole week in one picture. And the next steps is to have we can like how understand the core quantum computing principles, and how the basic projects can be done, and how these sessions can be adapted for your own students. So I'll be I'm share some resources and community. I have the where we can collaborate. I have built up the whole list, prepared I think a good exhaustive list, and I will be sharing it as a standalone document that you can see on the LMS, that where you can actually go through the learning materials, practicing how to do some practice in the Qiskit community. And there was one uh, Qiskit, IBM Qiskit summer school coming up in July itself. I think in mid-July. I'm not sure that it is open right now. I think it is closed. But yeah, if you were aware of that, then it is a good you can say way to go about it. Every resources from it will be uploaded on the YouTube, although you will not get a badge or something like that. But yeah, uh, IBM's Qiskit team each year like hosts this kind of workshop for 2 weeks. So yeah, we can join many other events like that. So yeah, that's it from my side. If there are any questions, yeah, I'm seeing the questions. Either everyone has like understood everything or they haven't understood. So yeah, I'm not sure. Ma'am, should we close our
Yeah.
session or something like that?
Yeah. Yes, sir. Thank you so much for wonderful 5 days of informative session, sir. We'll definitely be in touch for upcoming programs. Thank you so much, sir.
Okay, ma'am. Thank you very much. And, yeah, very. Uh, I would like to like extend my uh, uh, hearty thanks to the whole XLR team, because they were very uh, prompt in uh, discussing everything, right from very basic ideas. Sheetal ma'am, and the team, Nitya ma'am, and Amar sir. So thank you very much, the whole team, uh, and I look forward to other, you can say, engagements also. Thank
Yeah,
you.
definitely, sir. Thank you so much.
Thank you.
Thank you. Yeah, so dear faculty members, there are the updates which I will let you know right now. So I know you all like will having the question about the certificate. Yes, I'll let you know. So before that, some are asking for previous day's attendance link. The previous day's attendance link can be shared as we have intimated in the beginning. Attendance link will be active only for 1 hour, that is 4:30 to 5:30. So the previous day's attendance link can't be shared. So if you have not marked your all 4 days of attendance, I'm so sorry. I'm not like I can't share it again. Okay, so right now I'll let you know about the certificate. So after the completion of certificate, we require at least 10 to 15 working days to submit the certificate. So for your register mail ID, if you are eligible, like if you secured 60% or above 60% of attendance, for definitely you will all get the certificate for your register mail ID. About the materials and recordings and materials which is already uploaded in LMS. So whatever has been taught from day 1 to day 4, all the materials is uploaded in LMS. You can go through there and even the recordings. So yeah, the LMS access will be there. You can watch whenever you require. Have attended the lecture but unable to mark that. Okay, so attendance is very important where we you all have to mark your attendance at least for 3 days so that you will be eligible for 60% and 60% of attendance and you will be eligible for certificate. Okay, so yeah, this is what the program which we are going to complete today. And for upcoming program, if you are interested to join, we have the same EDL programs, which is CSR activities, where you can visit our website that is www.xlr.com and you can go through there whatever the program which we are doing on upcoming. You can click on registration link and register for your particular programs. And we do have a student development program as well, that is for students. If you're interested, you can inform your students as well. If you have attended in YouTube also you will be sharing a link every day. So yeah, it doesn't mean you have attended from Zoom or YouTube. If you have marked your attendance, if you fill the attendance form, for definitely you will be having a attendance percentage and you will be getting the certificate. And one more important thing, which this program is for faculty development, so it is for only for faculties. The students can join for the knowledge purpose, but they will not get the certificate. So yeah, uh, if you have attended as a student, you will be not getting the faculty development program certificate. Only for the knowledge purpose you would have attended. Each and every day in YouTube chat and also Zoom chat, we'll be posting the attendance link. Even a day one, we have posted the attendance link exactly at 4:30, and we have pinned that attendance link as well. Yeah, if it's required, you can view the recordings and materials in LMS portal. Any other question? You can just directly ping me in a chat. If any questions, I'll just address it. Okay, we have one particular mail ID that is edl@xlr.com. If any query or any issues, kindly drop a mail to edl@xlr.com. I'm just pinging the mail ID on chat, edl@xlr.com. Okay, I think there is no questions to be answered. So yeah, I hope the points which I have told it is clear. Fine. I think we can wind up this program for today. Thank you all. Thank you for joining all these 5 days. Thank you. We'll meet again in different programs. Thank you, everyone.